Hello, everyone. This is a continuation on the mathematical structure of quantum mechanics. And a minor announcement is that I will be starting a new series on computational and theoretical methods in astrophysics. This is because I am taking a computational physics class and an astrophysics class in my graduate school. So I want to not only teach the public, but also test my understanding on these topics. So I hope you look forward to that. And in this lecture, I will mainly talk about Lie groups and Lie algebras. And this topic is very important because I believe that Lie groups and Lie algebras are one of the most important topics in physics because they encompass a lot of intrinsic structures in both quantum mechanics and even things like general relativity. So let's go. The outline of this lecture is as follows. First, I'm going to summarize what we did in the last lecture. Then I'm going to first define what Lie groups and Lie algebras are. Then I will talk about the correspondence between Lie groups and Lie algebras. Excuse me. Then I will talk about applications of Lie groups and Lie algebras in quantum mechanics. And finally, as a bonus content, I will talk about Lie algebras and Lie groups in general relativity. In the last lecture, I mentioned that actually the funny thing is I was going to do this lecture last week, but then I realized that I did not talk about representation theory yet. So I decided to do representation theory first. So in the last lecture, I first defined what a representation is, and it is essentially a map from a group to a vector space. And I also defined what equivalent representations are. And essentially, equivalent representations are if there exists two different maps from a group to two different vector spaces, if they are related by a similarity transformation, then the representations are equivalent. But in the last lecture, I showed a very simple example where we have two similar matrices. But in general, the matrices need not be similar as long as you can find some matrix K and the inverse of it such that they satisfy this relation, then they are equivalent representations. Moreover, I defined invariant subspaces and irreducible representations. And apart from these definitions, I also talked about the relationship between irreducible representations and generators. And they are important because they transform the generators in physics transform the abstract mathematical property of groups and algebras into significant physical quantities, and we'll see some of these examples later. Moreover, I talked about the irreducible representations of SU2 and how they can be geometrically represented by a block sphere. And finally, I discussed how irreducible representations can determine the normal modes of vibration of a molecule. So let us get to the content of this lecture. So before I define Lie groups and Lie algebras, let me first talk about differentiable manifolds. So differentiable manifold M is a Hausdorff manifold. Basically, it's a manifold that is Hausdorff and is also secondly is a second countable topological space. Let me define what these terms mean. A Hausdorff manifold is a manifold where every neighborhood on the manifold is locally Euclidean. Additionally, a second countability means that the topological space has a countable base. Now, with that, I will define what a Lie group is. A Lie group is a group with a manifold structure such that a map F from to a group and a group to another group is and some elements and another map G from a group to a group, where the elements G frac 1 and G frac 2 are in G, such that they satisfy the multiplication rule and the inverse rule. And given that these two, if they satisfy these two and these operations are smooth, then this is a Lie group. So one example of a Lie group is the general linear group that I talked about in the last lecture. Maybe even actually the first lecture, sorry. And we have previously shown that the general linear group is a group. Now let us show that it satisfies the additional requirement for a Lie group. So first, we need to check that the binary operation is smooth. So the general linear group forms a non-abelian group under matrix multiplication. And since a matrix multiplication is a smooth operation, then this satisfies the condition that the multiplication is smooth. Moreover, since the inverse operation is also smooth, then the inverse multiplication in this section, in this not definition, but in this axiom here, is also smooth. Additionally, now we need to check that the general linear group is a smooth manifold. And to do so, we need to show that GL has a collection of charts such that the transition between the charts are smooth. Or in other words, GL has an atlas. The transition map between the charts are definitely smooth due to the smoothness of matrix multiplication and inversion. Therefore, GL has a collection of smooth charts such that the charts are the transition between the charts are smooth, and therefore GL is a smooth manifold. And well, let us digress a little bit and talk a little bit about the algebras. So this is a little bit more familiar because it is, I guess, in some sense less abstract. So a Lie algebra is a vector space over some field F, where there exists a binary operation known as the Lie bracket, denoted by this, such that it maps from two elements, to the vector space and the same vector space to the same vector space, and the elements in the vector space, basically x, y, and z, must satisfy the following condition. Basically, by linearity, basically it's similar to the linearity condition where it does this. Basically, sorry, what is this word? The coefficients can come out and the elements can be linearly superposed and added. Similarly, if you have it here, then you can do this same thing. It must satisfy alternativity. Basically, if you perform the Lie bracket on the same elements in the group, this yields 0. Next, it has to satisfy the Jacobi identity, where it has to satisfy this following property, and you can check this yourself. This indeed, if we have a, well, we haven't defined what a Lie bracket is, but we will see some examples later where this is true. And it must also satisfy anti-commutativity, basically where if you swap the order inside the Lie bracket, the arguments inside the Lie bracket, it should yield an additional negative sign. So one example of a typical Lie bracket is, well, it's not really a Lie bracket yet. It has to be a Lie bracket under a certain group. So, but you will see that the angular momenta forms a Lie algebra under the Poisson brackets, and the Poisson brackets act as the Lie brackets. So recall that the Poisson brackets of f and g is the partial of f with respect to the coordinate, and the partial derivative of g with respect to the conjugate momentum. And then you take the, basically you swap the arguments and then you get the following, similar to commutation relations. And so let me show that, I guess, angular momenta form a Lie algebra under the Poisson bracket. So let the one form be as follows. So basically x times the dx, and the momentum one form be as follows. Excuse me. So then the components of angular momentum in Rn, so basically any arbitrary dimensional space we define by Lij, can be written by the following two form. So basically we take x and p and we wedge product them together. So we get dxi, dxj, and then we get the following. And then the coefficient in front of the dxi and the dxj gives the angular momentum component. So since xi, which pj is satisfy. So basically, if you swap the wedge product, this satisfies the anti-commutativity property. So then the angular momentum component is written as follows, and you've probably already seen this. This is just the definition of angular momentum in R3. So this can be generalized to Rn. So let Lij be the elements of the vector space, then we need to check that it satisfies the axioms of the Lie algebra. So given that Lik, comma Ljk equals Lij, and Lij equals minus Lji, we can clearly see that it satisfies alternativity and the commutativity conditions. And also, given that the partial derivatives are linear operators, then the bilinearity condition is also satisfied. Moreover, we need to check the Jacobi identity. So let L be this quantity. So Lij plus this, and plus this. So basically, if you're working in R3, this can be X, Y, Z, and then you symmetrize them. So it'll be, you shift them by one, it will be Y, Z, X, and then it will be Z, Y, Z, X, and then it will be Z, X, Y. So we know the first term is as follows. So basically the first term yields 0. The second term, if we perform this calculation from here, from this identity, we know that this also yields 0. And the final term, we will check that using this same identity, it also yields 0. So L equals 0, and hence it satisfies the Jacobi identity. And we will revisit this example later. So you might ask, what is the relationship between Lie groups and Lie algebras? And the result is predicated on the following. Well, I hate using results twice. So the theorem, I guess, is predicated on the following results. So first one is Lie's third theorem, where all finite dimensional real Lie algebras are the Lie algebra of some simply connected group. The second one is the homomorphism theorem, where for Lie groups G and H, such that H is a subgroup of G, there exists a Lie algebra homomorphism from the elements of so basically from the Lie algebra G to H, such that there exists a unique Lie group homomorphism, F from G to H, such that phi is basically the differential of F. And the final one is the subgroup subalgebra theorem, where if H is a subalgebra of G, then H is a subgroup of G and has the algebra H. So the proof of the first and the third theorem is quite lengthy. So, and there are many books that show this, but I will not show it. I will only prove the second results and take the first and third theorem for granted. And I will show basically a geometric correspondence between the groups and the algebras. So give me a second. Let me have a drink of tea. Okay. So I'm going to show the correspondence between the groups and the algebras. So let the map from F from a group G to some other group H be defined as F of e to the x equals e to the phi x, where e to the x is known as the exponential map of G and has an inverse near the identity. So suppose that there exist two elements, e to the x and e to the y near the identity I, and let e to the z equal the multiplication between ex and ey. Well, if x and y are scalars, then we can just simply add the exponents together. But x and y can also be matrices, and this is not trivial. And you may have seen this before when you learned quantum mechanics. So we need to use a result called the Baker-Campbell-Hausdorff formula, or BCH for short. For e to the z equals e to the x times e to the y, the Baker-Campbell-Hausdorff formula is z equals x plus y plus half times the commutator plus some other nested commutator, and etc. To prove the before I actually state why we need this, let me prove the Baker-Campbell-Hausdorff formula. So to do this, we need another formula called the Hadamard formula, which is as follows. So basically, if we have e to the minus xi times x times y, e to the xi times x is equal to this following expression, again, where the dots represent the higher nested commutators of x and y. And to do so, we're going to prove both formulas, the Hadamard formula and the BHC formula. So if you have this as a homework problem, this video is perfect for you. To do this, we're going to use proof by induction. So let us first write this as a power series. So let f, basically we substitute this e to the minus xi x y, this as a power series, in K. So from the previous formula, we know that f of 0 is equal to y. So we can basically here, we can substitute 0 here, and then we get, so if we substitute k equals 0, we get 1 here, we get 1 here. So f of 0 is equal to, so basically this will be equal to y. So we need to check what f of 1 is. So f of 1 is simply d psi and sets psi to 0. And what we get is this. Then we get the following equation. And basically we take the derivative with respect to xi. So we get a minus xi, and we put the x on the left-hand side. And if we do this in this, if we do it in this way, we have to always multiply to the left-hand side. So we do it here, and here we multiply to the left. So we get here. So basically we take the derivative with respect to xi, right? So the x must come out, and then by product rule, we leave this the same. And then here, the x comes out here. So we multiply to the left. And if we factor out e to the minus xi, and we factor out this way, we get the commutator, and we set xi to 0. This will be e to the 0 and e to the 0, excuse me, which yields 1. So this will be the commutator of y and x. So now let us define another variable, multivariable function, basically with psi and k, such that this is such that it is equal to this. And this is simply e to the minus xi f of k times e to the xi of x. So basically it's the same thing, but we just have f of k in the middle. And from this, we can get an iterative relationship. So basically we get g to the xi comma k plus 1. It's just simply derivative with respect to of g with respect to xi. We get the following equation. Then we get e to the minus xi x f of k, commutator with x, e to the xi of x. And by setting xi to 0, we get g of 0, comma k plus 1. We get f of k plus 1. And hence f of k plus 1 is equal to f of k, comma x, which is the commutator this. Then by induction, basically, since we keep substituting these nested commutators in, we simply get the Hadamard formula. So from this, we can actually derive the Baker-Campbell-Hausdorff formula. And to do so, we let some variable h of xi be the following. Then what we do is we take the derivative with respect to xi. And here, we do the same thing. We take the derivative with respect to xi. We take x out and multiply on the left-hand side. And we do the same thing with y. We multiply on the left-hand side. Then we get the following. So basically, how I get from here to here, I multiply both sides. This is a mistake. Oh, no, this is not a mistake, sorry. What I do is I multiply, let's see what I did here. I first multiply both sides by e to the minus y. So here, this cancels, and this gets e to the minus y times e to the y. This gives the identity. Then what I do is I multiply both sides by e to the minus x. Xi x, so basically this cancels out, and then here we get e to the minus xi x, we get this formula. But remember from the Hadamard formula, we can substitute this as nested commutators of x and y. So we get the following. So basically we can divide both sides by h to get 1 over h dh dxi is equal to this. And we can see that this is a first order linear differential equation. And what we can do is simply solve this integral by, solve this integral by taking integrals with respect to xi on both sides. So we get the following here. And to get the formula we just saw, we can just set xi to 1. But we see that this is not exactly the form that we get in this theorem. So what do we have to do? So what we can do is before we were taking derivatives and multiplying by the left. We can do the same thing and take derivatives and multiply to the right. And what we get is this. So performing the same thing, I will multiply both sides first by e to the minus xi x. Then this will cancel out. Then I will multiply again to the left by e to the minus xi y. Then I get here. Then I get something that is similar to the previous differential equation, but instead I get e to the minus xi y x e to the xi y, and we have x in the middle. And then here we had y in the middle. So what we get is a similar differential equation. And by taking, basically, we can add them or subtract them to yield, we have to first add them together and then divide the result by 2 to get the following formula. And we can see that this is exactly the same as what we get here. Basically, here, we get the factor of 1 over 12 here. Because, in the previous case, we got a 1 over 6 here. By dividing by 2 and then adding them together, we get this factor here. So with this, we can compute the Lie algebra homomorphism by performing the exponential map onto this onto the group, and then what we get is the following: f of e to the x, e to the y. Then we get the following equation. It's basically the following map, and we can see that there is a homomorphism of the Lie group H, and we basically do this. We perform the map on e to the x and e to the y, and we get e to the phi x and e to the phi y, and we get f of ex and f of ey, and the homomorphism of f of ex, f of ey is equal to f of ex times f of ey between the groups G and H correspond to the homomorphism between the algebras G and H, such that phi is equal to the differential of the map. So basically what I've said just now is very abstract mathematics, but there's a very nice geometric interpretation of this. And basically, if we treat the Lie group as a manifold, then the Lie algebra is basically the tangent space on the manifold, and any basically any vector on the tangent space is any vector on the tangent space are elements in the algebra, and they are basically the generators. Basically, if you add these two together, so J1 and J2, you can get another element on the tangent space. So basically, let's say here, right? If you add these two, you get something like that is here. And by adding these two together, and we obtain a new element that is also on the tangent space, which means that it satisfies the axioms of the algebra. So this is quite nice. Basically, it's the geometric. So basically, by taking the differential map here, we see that the Lie group is the manifold, and the Lie algebra is simply the tangent space on this manifold. So this is a nice geometric interpretation of the correspondence between the groups and the algebras. So the reason why Lie groups and the algebras are so important, because they directly connect to the original symplectic definition of Noether's theorem in classical mechanics. So let me state what Noether's theorem states. Basically, the statement behind Noether's theorem originally, because originally Noether's theorem has nothing to do with, had nothing to do with Lie groups and the algebra. No one saw what the correspondence was. But later people saw that, oh, if we treat a Lie group as a differentiable manifold, then there is a correspondence between Noether's theorem and symmetries. So basically, let M be a smooth or differentiable manifold, and L be a smooth or differentiable Lagrangian, where T denotes the tangent space. Now, suppose that the couple, basically M comma L, admits a diffeomorphism of M to M. And remember, a diffeomorphism is just some kind of map that transforms from one manifold to another, or it can also be treated as a coordinate transformation. So where S is a real number and H0 is the identity. So if so, the Euler-Lagrange equation corresponding to the Lagrangian has first integral I, such that the map of the the tangent space map of M maps to a real number, and with local coordinates Q on M, and given by the following. So this is basically the first integral. So this is how Lie groups and Lie algebra relate to Noether's theorem. And by doing this, we find that Noether's theorem, Lie groups and Lie algebras are, because Noether's theorem is basically the language of symmetries, and they tell us symmetries correspond to conserved quantities. And now we know that Lie groups and Lie algebras are a more general definition, not really a definition, but a general language of symmetries in physics. So I've discussed the abstract mathematics of Lie groups and Lie algebras. Let me talk about some of the applications in quantum mechanics. So in quantum mechanics, Lie groups and algebras are essential, as the commutators usually serve as the Lie brackets, so long as the result is in the vector space. So the standard Lie group in quantum mechanics that are used are the HN group, which is the Heisenberg group, and has the algebras mathfrak HN, and there is the U1 group and has the algebra U1, SUN group, basically the associated and its associated Lie algebra is SUN, and SUON has basically special orthogonal group has the Lie algebra SON. And the above Lie groups and algebras have applications ranging from many topics in physics, from spin to addition of angular momentum. And I would go as far to say as Lie groups and Lie algebras are the essence of quantum mechanics. And I will even discuss their relevance to QFT, particle physics, supersymmetry, and as the bonus content in this lecture, general relativity. So first, let me talk about a crucial Lie group that gives rise to the uncertainty principle, namely the Heisenberg group. So the Heisenberg group, or H3, is a set of matrices given by the following expression. So here we can see that the matrix is obviously invertible, since its determinant is non-zero. Hence, H3 is a subgroup of the general linear group. And additionally, since the diagonal elements are 1, the determinant of the matrices associated with H3 is 1. Hence, H3 is a subgroup of the special linear group, and which is also a subset of the general linear group. And this is the reason why it is called the Heisenberg group, because it generates an algebra that is closely related to the commutator of the position and momentum operators. So we need to, in order to see this, we need to take the natural logarithm of the matrix associated with H3 and to find the Lie algebra. So the Lie algebra, if we take the logarithm, we get this, and where alpha is equal to A, beta is equal to B, and gamma is equal to this half AB plus C. So from equation 4.2, these represent the elements associated with the Lie algebra, HN. So to see this, we can write this as bases. Basically, we can take alpha. So basically, it's similar to what we did in the last lecture. We decompose them into invariant subspaces. So we do this. And let us denote X as the first matrix, Y as the second one, and Z as the third one. So from the equation, from the matrix that we saw in the previous equation, we can see that in equation 4.3, so we can see that they clearly satisfy the following commutation relation. So X comma Y is equal to XY minus YX is equal to Z. And the commutation relation with Z is equal to 0. And you may not see it yet, but if we write it as X is equal to X hat, Y is equal to P hat, and Z is equal to IH I hat, we obtain the commutation relation X comma P is equal to IH bar times the identity. So in the classical limit, H bar approaches 0, and we get the commutation relation between position and momentum. So basically, here we can see that you cannot measure position and momentum simultaneously. But if we take the classical limit as H approaches 0, there is no, the commutation relation is basically yields 0. And this yields an uncertainty of 0. So basically, we can measure a position and momentum simultaneously in classical mechanics. So this is an important relation. As mentioned in the previous lecture, the following two equations, we have the following two equations. Basically, f of x is equal to partial f with respect to x, I h bar, and we get a similar relationship with the momentum. And hence, if f of x and g of x are polynomial functions, then the set of all f of x and g of x are also form a Lie algebra. So basically, these are also part of the Lie groups. So now I will talk about another special group is UN. So UN groups have many applications. They have many wide applications in quantum mechanics. But one in particular is the U1 group, as it is responsible for giving rise to the Yang-Mills theory in electromagnetism. So let us look at the Lagrangian associated with the interaction of positrons and electrons. So we get the following Lagrangian, where psi is some spinor, gamma is the gamma matrices. Basically, it is it is a form of the Dirac, This is called the Dirac gamma matrix, and what happens is it has some association with the Pauli spin matrices. And A here is known as the 4 potential, which I have talked about in some of my other lectures on electromagnetism, and I've even talked about this in my derivation of the Reisen-Neustrom metric when I talk about the electromagnetic tensor. The first and second term correspond to the free fermion Lagrangian, and the third term corresponds to the interaction between. So basically, these two terms are basic. If you've seen this before, you've seen, this is just the first two terms are just the Dirac equation, and they correspond to free fermions. And the last term is basically the interaction is an interaction term between the positron and electron. So let us perform a U1 gauge transformation of the wave function. So basically, remember that e to the I phi is the e to the I theta is the theta representation of the U1 group, as the U1 group is just a set of all complex numbers with a modulus 1. So we can just write it as e to the I theta. So basically, by performing a U1 transformation, a U1 gauge transformation, we just multiply e to the I theta by psi. But if we take the complex conjugate, we have to multiply e to the I theta to the other side, and we have to take the complex conjugate. So plugging these transformations into the we yield a transformation of the Lagrangian. So we get the following. So basically, it's as I said, basically here, I just replace e to the psi bar with this, and the psi with this, and we get this. So basically, we can see in this term, they cancel out. So basically, e to the I minus I theta times e to the I theta is just 1. Here, we get something similar. It's also just 1 because these two are scalars, and scalars can just be multiplied outside if we have a matrix in between. So that's fine. But we notice here that if we take a partial derivative with respect to e to the I theta, we get this additional term. And this kind of ruins the Lagrangian because it is almost invariant, but the derivative term has an extra part, e to I phi times a partial mu of theta. So believe it or not, we can actually just fix this by transforming the 4 potential in the following manner. So a mu to a mu plus I partial mu of theta, and basically if you add this here, you can see that these basically cancel out. And what's very interesting is that in particle physics, when we add extra fields, this corresponds to adding a new particle. And miraculously, this new particle that we have introduced is the photon. And thus, this implies that U1 gauge invariance gives rise to photons. And the physical implication of this is that the electromagnetic force is mediated by the photon. So basically, in particle physics, the interaction between particles are always mediated by a force, and namely, these forces are mediated by gauge bosons. So there are 3 known gauge bosons, and 1 is predicted. So 1 is the photon, which is the electromagnetism. The weak force is mediated by the W and Z bosons. The strong force is mediated by gluons. And the final one we don't know of is gravity. It's quite mysterious. we have not yet detected a graviton, but we suspect that it exists. So this is an image of a Feynman diagram where basically we have an electron interacting with another electron, and what it does is it mediates a photon. So maybe I should lighten all this difficult mathematics with some humor. One of my friends, or actually one of my professors in university, said, it is not God that said, let there be light. He said, let U1 gauge invariance. God said, let there be U1 gauge invariance. And yeah, basically this is why there is light in physics. So now that I've talked about U1 groups, let us talk about SUN groups. And there's a nice connection with something that I've previously discussed, namely angular momenta. And under quantization, the Poisson brackets in classical mechanics are replaced with commutators in quantum mechanics. And thus the Lie algebra is as follows. And the Lie algebra tells us the generators of the Lie group. And by finding the generators, we can determine the irreducible representations. And from this, one can deduce the group structure. And we will find that this is indeed part of SU2. However, there is an even cooler, I will talk about this later when I actually talk about angular momenta, but there is an even cooler correspondence with quantum entanglement. I will discuss this very briefly, and I will save the in-depth discussion for Simba in his quantum computation and information course. So before we can talk about quantum entanglement, we need to first define a tensor product representation of a group. So it is defined as follows. So let phi of V and phi of W. Basically, these two are representations that map a group G, the same group G, to different vector spaces V and W. But these vector spaces can be the same. Basically, there exists a tensor product representation as follows, such that it is the tensor product representation of V onto G with the representation of W onto G, where G are elements of the group big G. So now let us see what happens to its Lie algebra representation. So to do so, we simply take the derivative of the exponential map. So basically, we just take we define a new representation, 5 prime. We take the derivative with respect to lambda and take the exponential map. And what we do is we perform this, use this definition here, put the exponential map into G. And what we get is this. And what we find is that this new tensor product representation is equal to the representation tensor product with the unit matrix, the identity matrix, the tensor product representation of the identity matrix with dimension V, and the identity matrix with, added with the identity matrix with dimension W, tensor product with the vector space, the representation of the vector space W. So let us talk a little bit about decomposability. So basically, a vector in this new vector space is decomposable if it can be written as V, tensor product W, with V in capital V and W in capital W. And if it cannot be written as such, it is a composite vector. So this is important because if this is a not this, but like if this is a composite, maybe this is not the right way to say it. If this is a composite vector, then it is an entangled state, as it cannot be written as a tensor product of two different vectors. Moreover, there is an amazing link between entanglement and the addition of angular momentum. When I discuss the addition of angular momentum in the future, I will prove the following theorem, but I'll just state it right now. So this is the Clebsch-Gordon decomposition. So the tensor product defined by the following couple can be decomposed into irreducible representations as follows. So basically here, we have the representation of n and n plus 2 and the vector space n1, the representation of n1 plus n2 with the vector space n1 plus n2. if we take the direct product of these, we can decompose this tensor product representation. So if you have done particle physics before and quantum mechanics, you would have seen this very, very it's basically a monstrosity. It's a table of Clebsch-Gordon coefficients, and this is how we obtain things like addition of angular momentum in quantum mechanics, because in quantum mechanics, angular momentum does not add trivially. So we need to determine the Clebsch-Gordon coefficients. And if you've done quantum mechanics before, you've probably seen this. And this basically is where it comes from. This is why I say quantum mechanics is the essence of group theory and representation theory is the essence of quantum mechanics, because this Clebsch-Gordon coefficients are related to this Clebsch-Gordon decomposition. So what does this have to do with entanglement? So in the last lecture, Simba has talked about Bell states, and one example is the following. So mathematically, these are examples of entangled states because they cannot be decomposed. And physically, since they are not decomposable, the states are composite, which means they are dependent on each other. This means, let's say you have a particle of spin up and a particle of spin. Basically, we don't know what their spin is yet, but they are entangled. If we measure this as a spin up, this one must be spin down. So the reason why they are entangled states is because they are dependent on each other. And this means that the change in one state will automatically alter the other. But if they were not entangled, this can be spin up and this can be any arbitrary spin. So basically, this is why entangled states are basically composite vectors. So linking this back to Clebsch-Gordon coefficients, if you cannot perform a Clebsch-Gordon decomposition on a state, this means that they are entangled. And basically, this is why that you can have one spin up and one spin. So basically, if they're entangled, they have to be dependent on each other. But it is important to note that decomposability is basis dependent, meaning that just because it cannot be decomposed in one particular basis does not mean it cannot be decomposed in another basis. So in order to prove something is an entangled state, there's many ways to do it. A symbol will talk about another way to do it. But the way that I like to think of it is that we can write these vectors as coordinate-free representations. And by doing this, if you can show that even in the coordinate-free representation that these cannot be written as a tensor product, then there is no basis that you can choose such that these are not entangled. Sorry. So basically, if you show that even in the coordinate-free representation, you cannot write this as the tensor product of two states, this shows that they are entangled. So another group that, the final one that I'm going to talk about before I talk about general relativity is the SO3 group, as it is closely associated with rotations in 3 dimensions. Hence, it is related to the wave function of the hydrogen atom and spin in quantum mechanics. So recall that for an n by n matrix A times A transpose is equal to A transpose times A is equal to identity. And this is equal to, the determinant of A is equal to 1. So this is the set of these kinds of matrices are part of the SON group. So thus, one matrix that is part of the set is the skew matrix, skew symmetric matrix that are written as follows. So skew symmetric matrices have the following expression. So we can also decompose this into invariant subspaces. So basically, we factor out Z and then do the following. So we factor out Z and X and get the following invariant subspaces. And these are the generators of the Lie algebra SO3. So one can write this as omega x times Lx, y times Ly, and Z times Lz. So basically, this is Lx, this is Ly, and this is Lz. So the invariant subspaces are the generators of the SO3 group as they satisfy the Lie algebra, the following Lie algebra. And one will notice that these are the angular momentum operators in quantum mechanics. So therefore, the angular momentum operators are the generators of the SO3 group. However, this is not the end of the story. As we can see that the angular momentum use the angular momentum operators to calculate spherical harmonics. So this is because in spherical coordinates, if we act LZ on the spherical harmonic, we get minus I partial phi of this, which is equal to m of this. And basically, this is just simply a simple partial differential equation. We can just separate into phi and theta parts, and we will find that and divide both sides by the theta part, and we will find that partial of phi of the phi part is equal to m of phi, and this is simply just e to the im phi. So basically, the phi part is just e to the im phi. So basically, we know that ylm is equal to e to the im phi times f of theta. Now, if we act the following operator, Lx plus Ily on Lm, and doing this in spherical coordinates, we get the following expression. And by solving, so once again, if you know what this is, you can solve this differential equation, and we get Ylm is equal to this, where Clm is some coefficient. And I will derive this in more detail when I discuss the symmetries of the hydrogen atom. But more importantly, what does this mean? Excuse me. Well, this means that the spherical harmonics are the integral representations of the SO3 group. And spherical harmonics are important because they are typically the angular solutions of spherically symmetric systems. Like if you have the Laplace equation, the Poisson equation, or the wave equation, you will definitely encounter spherical harmonics. And you will see that in classical mechanics, you will see them in many different areas of physics, namely classical mechanics, when you for example, if you want to solve for the Laplace equation for fluids for spherically symmetric systems, you will get these spherical harmonics if they have some phi or theta dependence. In electromagnetism, you will definitely have seen this if you solve the Laplace equation or the wave equation of the Poisson equation for the electric potential. Quantum mechanics, as I said before, you will solve it for the hydrogen atom. And even in general relativity, you will need the spherical harmonics when you solve for example, if you want to derive the wave equation in a curved space-time and show that black holes radiate. You have to use black hole superradiance, solve the wave equation in curved space-time, and you will definitely see the spherical harmonics. So as a bonus content, I will now talk about connections to general relativity. So before I talk about general relativity, there is a nice connection between groups and vectors and tensors. If you are a physicist and you ask them what the definition of a vector or tensor is, they will probably say something like, oh, a vector or tensor is something that transforms like a vector or tensor. This statement may seem tautological, but let me try to demystify what they actually mean. So this should be a vector. Sorry, this is a mistake. This word should be vector. A vector can be characterized by the following transformation law. So basically, v bar of I is equal to the partial derivative of I of this coordinate x bar over the partial derivative of xj and vj. So basically, this is known as Jacobian, and it is responsible for changing coordinates from one system to another. But in multivariable calculus, you have probably seen this coordinate transformation from Cartesian to polar. For a unit circle, it is as follows. And what we clearly see is that this is a way of writing the elements of the SO2 group. So basically, this is just the set of rotational matrices. And in general, an n-dimensional vector transforms under the SON transformations. So for Lorentz vectors, for example, in relativity, you have the -1 index on the time component. So we have a new kind of transformation it's called SOP, Q, and this is called the Lorentz. This is the Lorentz group. So basically, this is what it means when people say when a vector transforms like a vector, because a vector transforms under something called SON transformation. So they just rotate. How about tensors? So basically, a tensor transforms as follows. So basically, we have the same thing, but we have multiple partial derivatives, so multiple Jacobians. So we can see that a tensor transforms in a similar manner, but we have multiple SON transformations. And similarly for Lorentz vectors, there are multiple SOP, Q transformations where P, Q is equal to n. And when a physicist say a tensor transform is something that transforms like a tensor, it means that they have multiple SON transformations. So since general relativity heavily utilizes tensors, group theory is immensely important. However, there are more novel uses for group theory in general relativity, namely when discussing conserved quantities in a metric. So in differential geometry, when we describe a parallel transport of a quantity along a vector x alpha, we describe it by the Lie derivative. So basically, the Lie derivative of xa alpha of the vector y beta is as follows. So basically, x alpha contracted with the covariant derivative. We do the same thing with the y component, and if we let this x is equal to x alpha, covariant derivative alpha, and y beta contracted with the covariant derivative y beta, then we will find that L of x of y is equal to x comma y, and here this Lie bracket is denoted as the commutator. And this is really cool because we see that the Lie derivative and parallel transport has a structure of a Lie algebra, which kind of makes sense because we talked about, we defined the Lie groups in the context of differentiable manifolds. So this, you may think it is mysterious, but we will see that, we can see that actually it kind of makes sense. So what will be more interesting later is when we discuss how it helps us determine conserved quantities in the form of Killing vectors. So in general relativity, a Killing vector is defined when a Lie derivative of a metric is set to 0. So basically, I take the Lie derivative of a metric, and we get this. And by definition, we know the first term vanishes as the covariant derivative of a metric is always 0. And the second term, because the covariant derivative of the metric is 0, we can basically put the G alpha gamma inside, and what we get is, and we contract alpha with alpha to get xi gamma, and then we get something called the Killing equation, which is this, basically where xi is now called the Killing vector, and we will notice that this forms a Lie algebra under anti-commutation. So basically this forms a special kind of algebra called a Clifford algebra, which I will discuss later when I talk about supersymmetry. So if the equation above is satisfied, this is a Killing vector, but what is the connection to Lie groups? So let us illustrate this with an example. So we will talk about flat space-time first. So recall that in 3 + 1 dimensional Minkowski metric, a Minkowski metric, so basically this +1 denotes the negative time dimension. So we get this, and we can see that for Minkowski space, the Killing equation is a partial differential equation, which has general solution as follows, where n alpha beta and c alpha are constant tensors and vectors respectively. So one can see that the metric is not dependent on any coordinates. So the constant vectors are simply the basis vectors. So basically partial t, partial x, partial y, and partial z. Basically, these are ex, et, ey, and ez. So basically, one can show that the linear combination of these vectors are also Killing vectors as they satisfy the Killing equation. Here, the Killing vector partial t is associated with the conservation of energy, as we discussed in the previous, maybe the first lecture. Time symmetry corresponds to conservation of energy, and x, y, and z corresponds to conservation of linear momentum. Additionally, the Killing equation, by the Killing equation, n alpha beta has to be antisymmetric, and because it is antisymmetric, it must be traceless. So we get the following equation. And since there are 6 degrees of freedom, because since it's antisymmetric, we only have these 6 independent components. This means that the space is 6-dimensional, so that the invariant subspace is 6-dimensional, as the linearly independent vectors span the space. So these 6 vectors, linearly independent vectors, span the space. And thus we can find these vectors by decomposing into n alpha beta. So we can decompose this tensor n alpha beta by using the previous concept of linearly independent subspaces, where I take n0, 1 factored out, and then we add it together. So these are the dimensions of this matrix, and so these are the invariant subspaces of the matrix, and this matrix is thus 6-dimensional. We can do this, and hence all the elements in the lower left-hand corner are -1, and these are +1. We can just set them to 1 to make them the unit basis. So we can see that the 3 vectors are associated with purely spatial components. So we get this, basically ji is equal to the vis-a-vis symbol of partial I and k, and we get the following equation. And we can see that this looks very familiar. This looks like the angular momentum vectors. And therefore, we call these the Killing vectors associated with rotation. More importantly, the Killing vectors corresponds to the conservation of angular momentum. Additionally, there are 3 components with mixed time and space components. So basically, let's look back, right? Yes, here. So basically, these 3 components are the purely spatial ones, and these 3 are the time and space mixed together, because these are the 0, 1 components, and these are the 0, n components, and these are the basically ij components. So what we get here is we have 3 vectors associated with rotations. There are another 3 components with the mixed time and space components, and these perform time translations, and thus they are called the Killing vectors associated with boosts. And there is a more generalized form of the previous. It is a more generalized form of the previous conservation laws. It tells us in general relativity, we can always write energy and momentum as a 4 momenta. So this corresponds to the conservation of 4 momentum. So recall that the generators of a Lie group are the elements associated with the Lie algebras. So you will find that the Killing vectors of Minkowski space are the generators of the Lorentz group, SO1, 3. This implies that they are the elements of the Lorentz algebra. And in terms of vectors, the generators can be thought of as the bases for the vectors that form the Lie algebra. Moreover, since the generators are typically written as matrices or vector fields, they can be obtained by taking derivatives of the group elements with respect to the group parameters. And as a result, the generators correspond to the infinitesimal transformations of the Lie group. This means that the infinitesimal transformations of the coordinate associated with the corresponding Killing vector leaves the metric invariant. Connecting this to the last lecture, the irreducible representations of the Lie group can be constructed by exponentiating the generators and applying the resulting group elements to the vector in the representation space. This is because the generators of the Lie group can be identified with the tangent vectors at the identity element of the group. Thus, these generators together with the commutation relation encode the Lie algebra and determine the structure of the group. Well, a minor spoiler alert is that the irreducible representations of the Lorentz group have a cool connection with the Pauli matrices in quantum mechanics. So therefore, the SO1, 3 group is isomorphic, isomorphic to the SU2 group. We have already talked about Minkowski space. Let us talk about a more interesting example related to black holes. So recall that the Schwarzschild metric is as follows. So the natural question to ask is, does this have a Lie group structure with an associated Lie algebra? Well, to answer this, let us find the Killing vectors. So we see that the metric is not dependent on t, theta, and phi. And therefore, we can use a similar argument to that of Minkowski space and deduce that the Killing vectors are partial t, partial theta, and partial phi. And if we write this, the Minkowski metric in spherical coordinates, we find the following. And this means that the Killing vectors, partial phi and partial theta, are identical to that of Minkowski space, as they are the generators associated with rotation. So previously, I've talked about the mathematics behind the generator of rotation. Now I have illustrative examples of why these are called the generators. So as we can see, the yellow arrows represent the the Killing vectors, and the blue sphere represents the space. So we can see that the Killing vectors actually generate rotation. But I have to note something important. This does not mean that the black hole is rotating. This just means that the Killing vectors generate rotation, and it means that the black hole is invariant under rotational transformations. This is what it means for something to be spherically symmetric. So basically, if you have a sphere and you close your eyes and you'll see, oh, if I rotate the sphere by some angle, then there is no, basically, I can't distinguish whether the sphere has been rotated. So this is what it means to be spherically symmetric, but this does not mean that the black hole is rotating itself. We will discuss rotating black holes in my black hole series when I get to the current metric. So this is quite nice. We can see that this is the reason why we call it a rotational killing vector and why we call it the generators of rotation, because they actually generate rotation on a sphere. So how about the generators associated with boost? Unfortunately, in the equation, we can see back here, there is R dependence. So there's a dependence on R. And if we convert this to Minkowski space, there's a dependence on X, Y, and Z. This means that there are no generators associated with boost apart from the partial t component, because this metric is a static metric, as I showed in my lecture on Birkhoff's theorem and the Schwarzschild metric. Basically, spherical symmetry implies that vacuum solutions to the Einstein equation are static. So here, since the generators, since there are no generators associated with boost apart from partial t, this means that the form momentum is not conserved, and that is to say that the energy is conserved, but the linear momentum is not. This means that the group of isometries of the Schwarzschild metric has 4 generators, and it's associated with a Lie algebra with 4 elements. This means that the group of isometries of the Schwarzschild metric is not a group of SO1, 3, but it is a subgroup of a more generalized group called IO, and this is informally dubbed, I think this is called the Poincaré group, sorry. The IO group is called the Poincaré group, and this is informally dubbed as the inhomogeneous group, as the Poincaré algebra contains no inhomogeneous term. Contains inhomogeneous terms. So why are Killing vectors important? Because they determine intrinsic physical quantities. For example, for black holes, the surface gravity is given by the following expression, where xi is the Killing vector. So basically, we can, using the Killing equation, we can write this as xi I comma j, basically take the commutator and multiply by a factor of 1/2. Then we get this equation where kappa here is the surface gravity. So for the Schwarzschild metric, xi of I is equal to partial t, is equal to this. And the reason why there's a 1 here is because I write this in null coordinates or Eddington-Finkelstein coordinates. If you do this in standard Schwarzschild, you'll get a mess. So don't try it. But by doing this, we get kappa is equal to the following expression. So partial r of this, taking the derivative with respect to r, we get this, and substituting r equals 2m, we get 1/4m. And if we insert the dimensions in, we will find that the surface gravity indicates that it tells us what the acceleration due to gravity at the surface of the black hole. This is very important because this means that the gravitational acceleration on the surface of larger black holes is smaller than that of less massive black holes, which was kind of mind-blowing to me when I knew it, because I thought that more mass means the stronger gravity. But but this is not the case. We can see that if m increases, the surface gravity decreases. But there's something even more interesting, because when I will talk about QFT in curved spacetime and derive the Hawking temperature, we will find that kappa is directly proportional to the temperature of the black hole. In fact, T is equal to kappa over 2 pi, which means that for larger black holes, the temperature is much lower. And for smaller black holes, the temperature is much higher. So that concludes what I have to say in this lecture. And in the next lecture, I will actually start to talk about quantum mechanics, because I have done all the prerequisites, the mathematical prerequisites for to actually discuss quantum mechanics. And additionally, as I said before, I will start to do another lecture series on computational and theoretical methods in astrophysics. So I hope you look forward to that. I hope you learned something, and I'll see you in the next lecture. Thank you.